All right, good morning, guys. Let's go ahead and get started. Today we're covering 5.3, properties of quadrilaterals. Our learning target is 5.5. I can prove properties of parallelograms, and I can solve problems using properties of parallelograms. Let's go ahead and jump right in. So first off, these are all the properties of parallelograms that we've covered in our past videos. And the reason why this is important is because we're going to be using a lot of these properties to solve these application type problems. And we can also use all of these properties within our proofs as well, which is really useful for us because as we're going through, and if they only give me a parallelogram to start a proof, well, I can use all of these properties to further along my proof then. So that's why this is really important and really useful to know, because we can use all of these in our proofs, but also we can use them to solve application problems. So let's go ahead and see our first proof of the day. We're given that ABCD is a parallelogram. We're given that angle GHA is congruent to angle FEC, and segment HB is congruent to segment DE. What we would like to prove is segment GH and EF are congruent. So of course we start off with our givens, and we draw them in as we go. Now, since this is a parallelogram, we can use any of the properties of parallelograms that we'd like. The one that I'm going to go ahead and use is I'm going to use that opposite sides of a parallelogram are parallel, the definition of a parallelogram. So I'm going to say that DC is parallel to AB. And again, the reason that we can say that is if a quadrilateral is a parallelogram, then opposite sides are parallel. Now, the reason I did that is because I want to prove that these two triangles are congruent. Because if I can prove that these two triangles are congruent, then GH will be congruent to EF. So, since these two sides are parallel, DC and AB, that means that segment AC is a transversal line. So there's going to be a relationship between angle GAH and angle FCE. And that relationship is that they're alternate because they're on opposite sides of our transversal, and they're inside our parallel lines, so they're alternate interior angles. And we know that if we have parallel lines, then alternate interior angles are congruent. So I can say angle GAH is congruent to angle FCE. And again, the reason that we can say that is because if we have parallel lines, which we do from statement number 4, then alternate interior angles are congruent. Lastly, we just need AH and EC in order to prove that these two triangles are congruent. Or we need FC and AG. I'm going to go ahead and stick with AH and EC though. I think that'll be a little bit easier. So, again, I'm going to go back to a parallelogram because I have all these properties that I can pull from with a parallelogram. The next property that I'm going to use is that opposite sides of a parallelogram are congruent. So I'm now going to say that DC is congruent to AB, the entire thing. And again, the reason that we can say that is because opposite sides of a parallelogram are congruent. Now, once we have this, that these whole sides are congruent, well, let's say I just want AH. I know that AB, we have AB, and we have HB. What can I do to get AH from that? What if I take away HB from AB? Well, then I'd just be left with AH. So AH is congruent to EC. AH is congruent to EC. And the reason that we can say that is we're just taking away a segment. Well, what's another term for that in terms of properties? Well, that's the subtraction property. So we just subtracted those segments. Well, now looking at this, I can start anywhere on my triangle, and I'm just going to go ahead and look for congruency signs. I see angle, side, angle. So therefore, I can say that triangle AHG is congruent to triangle CEF by angle, side, angle. That's exactly what we were trying to do earlier. So now that we know that these two triangles are congruent, we can finally say that GH is congruent to EF, and the reason that we can say that is because if triangles are congruent, GH is second and third, EF is second and third, so those are corresponding parts, and we know that corresponding parts of congruent triangles are congruent. With that, this proof is done. All right, next up, we have another proof. Given parallelogram ABCD, prove that AC and BD bisect each other. So essentially we need to prove that BE is congruent to ED and AE is congruent to EC. Now as we look at this proof, we see that there's already numbers for angles. So that tells us, that's a big hint right away. We're going to be using those numbers in this proof somewhere. So of course we're going to start this off by using our given. parallelogram ABCD. From here, we have all those properties that we can take from. Now, I'm not going to use opposite angles are congruent because that'd be the whole angle, right? And I just want angle 1. So instead, what I'm going to do is I'm going to focus on the sides. I'm going to say that opposite sides are parallel. So I'm going to say that AB is parallel to DC and AD is parallel to BC because we know that opposite sides of a parallelogram are parallel. What this does is this now gives us these diagonals as transversal lines. So if I look at this, what's the relationship between angle 1 and angle 2? Well, if BD is a transversal, they're on opposite sides of the transversal, so they're alternate. They're inside the parallel line, so they're interior, so they're alternate interior angles. And we know that if we have parallel lines, which we see in statement number 2, that alternate interior angles are congruent. So I can say that angle 1 is congruent to angle 2. Are there any other angles that are up here that have that same relationship? Well, yeah, 3 and 4. Those are also alternate interior angles. So angle 1 is congruent to angle 2, angle 3 is congruent to angle 4, because parallel lines imply that alternate interior angles are congruent. Now looking at this, we have 2 angles. We now need a side, either BE or EC, or BC. So if we can find any side here, we essentially have proven that the triangles are congruent. So again, I'm going to go back to a parallelogram. What property of a parallelogram will give me one of these sides? That isn't that the diagonals bisect each other, because that's what we're trying to prove. I can't use that property here. Well, how about opposite sides are congruent? So I can say AD is congruent to BC, and the reason that we can say that is because opposite sides of a parallelogram are congruent. From here, if we look at this, we have angle, side, angle. So these 2 triangles are congruent. These 2 triangles are congruent by angle, side, angle. So triangle ADE is congruent to triangle CBE by angle, side, angle. Now, if the triangles are congruent, that means that corresponding parts are congruent. So I can say that BE is congruent to ED and AE is congruent to EC. And the reason that we can say that those segments are congruent is because if the triangles are congruent, then the corresponding parts of congruent triangles are also congruent. If that's true, well, BE is now congruent to ED, so that means that BD is being bisected. AE is congruent to EC, so AC is being bisected. So we can now say that AC and BD bisect each other. Because if 2 segments divide each other equally, then the segments bisect each other. And with that, this proof is finished. All right, let's go ahead and move on. Next up, we have some application problems. Our first application problem is to find the perimeter of the kite. So in a kite, I know consecutive sides are congruent to each other. So CB is congruent to BF, FD is congruent to CD. So I'm going to go ahead and solve for X and Y in this problem just so that we get the practice in for it. But there is an easy way to solve for this because we know that consecutive sides are congruent. So I can just be like, oh, well, this would be 20, this would be 12. I can just now add them all up. But again, just for practice's sake, I'm going to go ahead and go through this problem. So again, we know consecutive sides are congruent, so I can go ahead and set up all my sides. And this will allow me to set up 2 equations. So I have my red equation, 3x plus 4y equals 12. My blue equation, x plus 2y equals 20. So those are my 2 equations that we have. Now, since they both have 2 different variables, x and y, we have a system of equations. And so we're going to need to actually solve this system of equations through elimination or substitution. I'm going to go ahead and use elimination here. So I need my coefficients, the number in front of the y values, to be opposite numbers. So if this is positive 4 up here, I need to change this positive 2 to a negative 4. So what can I multiply positive 2 by to get to negative 4? Well, I can multiply by negative 2. So my top equation remains the same, 3x plus 4y equals 12. My bottom equation is multiplied by negative 2. So I have negative 2x minus 4y equals negative 40. From here, I'm just going to go ahead and combine straight down. My 4y's will cancel. My x's, I'll just be left with a single x, so I now have x equals negative 28. I can then plug this back in and solve for the y variable. So plugging negative 28 back into my blue equation, I have negative 28 plus 2y equals 20. Adding 28 to both sides gives me 2y equals 48, so therefore y is equal to 24. Now that we have both x and y, we can go ahead and plug them back in. And in fact, we would get 20 for CD, and we'd get 12 for CB. So therefore, our final answer is 20 plus 20 plus 12 plus 12, because again, perimeter is just the entire thing added together, which will give us a total of 64 units. All right, next up. Again, same type of problem. We're going to go ahead and solve for x and y, and then we're going to find the perimeter. So same thing, the disjoint pairs of consecutive sides are congruent. So 3x minus y equals x plus 3. 2x minus 1 equals x plus 4. So we now have two different equations that we can use. So from here, we need to determine which one we want to solve for first, the blue equation or the red equation. Looking at the red equation, I have two variables, x and y. Looking at the blue equation, I have one variable, x. So I'll go ahead and solve the blue equation first. I'm going to go ahead and subtract an x from both sides and add a 1 to both sides, giving me x equals positive 5. And I can plug that 5 into our other equation to solve for x, which will give me 3 times 15 minus y equals, 3 times 5 minus y equals 5 plus 3. 15 minus y equals 8, and then subtracting 15 from both sides gives me negative y equals negative 7. Of course, I can't have a negative out front here, so I need to divide both sides by negative 1. That'll give me y equals positive 7. Now that we have both x and y, we can go ahead and find the perimeter. All I needed for the perimeter, though, was x. So if I plug x back in, I get my blue side as 9. And my red side is 5 plus 3, which would be 8. So my perimeter is 9 plus 9 plus 8 plus 8, which will give us a total of 34 units. All right, next up, we want to find the perimeter of this parallelogram. So the property that we want to use for this parallelogram is that opposite sides are congruent. So therefore, I'm going to have x plus 5 equal to 2x plus 1. And I'll have this top side, x plus 9, congruent to the bottom side. So from here, we can go ahead and solve this equation. I can subtract an x from both sides, subtract a 1 from both sides, giving us x equals 4. Plugging x back in, my blue side will be 2 times 4, which is 8, plus 1, which is 9. So the blue sides are both 9. And the red side is 4 plus 9, which is just 13. So therefore, our perimeter is 9 plus 9 plus 13 plus 13, which will give us a grand total of 44 units. All right, our next application problem. In the parallelogram ABCD, we want to find angle D and angle C. So since this is a parallelogram, I know consecutive angles will be supplementary because they're same side interior angles. So if angle A is x and angle D is 3x minus 4, I can add these two angles together and set it equal to 180 degrees. From here I can solve for x, giving me 4x equals 184, and then I can divide both sides by 4, giving us x equals 46. Once I have x, I can go ahead and plug it back in. Well, since I know angle A and angle D are supplementary, I can do 180 degrees minus angle A, which is 46 degrees, and that will give me angle D. Also, angle A and angle C, these are opposite angles. And we know in a parallelogram, opposite angles are congruent. So if angle A is x degrees and x is 46, then angle A is 46 degrees, which means that angle C is also 46 degrees. So angle C is 46, meanwhile angle D will be 180 degrees minus 46, which gives us 134 degrees total. All right, here is our last proof of the day, and then we're going to have a couple true or false questions to finish it off. So we're given rectangle MPRS. We're also given that MO is congruent to OP. We'd like to prove that triangle ROS is isosceles, meaning that at least two sides are congruent. So to prove this, we either need SO congruent to RO, or we need angle RSO congruent to angle ORS. One of those two things needs to happen here. So to get started on this, of course, we're going to start with our given. MPRS is a rectangle, and MO is congruent to PO. Now, from here, since it's a rectangle, rectangles have their own unique properties. One of those is that diagonals are congruent, but we don't have any diagonals drawn. So therefore, I'm going to use my other property, that a rectangle has 4 right angles. So I'm going to go ahead and say that angle SMO and angle RPO are right angles. The reason that we can say that is because it is a rectangle, and a rectangle has 4 right angles. Since the rectangle is within the parallelogram family, it also holds all the properties of parallelograms. That includes that opposite sides are congruent. So I can say that SM is congruent to RP because opposite sides of a parallelogram are congruent. From here, this should be enough to prove that the 2 triangles are congruent to each other. If I look at this, I can go ahead and start on any side length that doesn't have congruency, and I work my way towards one. My first congruency mark is a side, then we followed by an angle, followed by a side. So therefore, triangle SMO is congruent to triangle RPO by side, angle, side. If the 2 triangles are congruent, well, I see S and O are first and third, R and O are first and third, so I can say SO is congruent to RO, because if triangles are congruent, then the corresponding parts are congruent. Since SO is first and third and RO is first and third, those are corresponding parts. So therefore, they're congruent by CPCTC. Corresponding parts of congruent triangles are congruent. Well, that's what we needed to prove, because if these 2 sides are congruent, that means that this is an isosceles triangle. So triangle ROS is isosceles because if at least 2 sides of a triangle are congruent, then the triangle is isosceles. And with that, this proof is finished. All right, next up we have some true or false questions. The first one that we have is true or false, all trapezoids are parallelograms. Well, by definition, this is false. If we look at the definition of each, a trapezoid has 1 pair of parallel sides. Meanwhile, a parallelogram has 2 pairs of parallel sides. So therefore, since a trapezoid cannot have 2 pairs, or else it would no longer be a trapezoid, this will always be false. Next up, true or false? No rectangle is a rhombus. In order to answer this, let's go ahead and draw a little Venn diagram. So here's our parallelogram family. We have rectangles, rhombi, and squares within that family. So we're going to go ahead and look at rectangles. Is a rectangle ever intersecting the rhombus? Well, yes, they intersect at squares. So this is false. A square is both a rectangle and a rhombus. So as a result, that is the only time that rectangles and rhombi are the same, is when they're squares. All right, next up, true or false? All parallelograms are quadrilaterals. So to answer this, we're going to go ahead and draw the quadrilateral family, which includes the parallelograms as well. So we still have that parallelogram family from earlier, and this time we have the trapezoids in and the kites as well. So all parallelograms are quadrilaterals. If I look at parallelograms, they fall within the quadrilateral giant rectangle here. So therefore, every single type of parallelogram is definitely going to be a quadrilateral, because all parallelograms are part of the quadrilateral family. All right, 2 more. True or false, some isosceles trapezoids are parallelograms. So again, if we draw these families up, you'll notice that we have isosceles trapezoids on the left over here. Parallelograms are over here on the right. There is no intersection at all of trapezoids or parallelograms, so this is false. The only thing that is true about both of these that they have in common is that they're both quadrilaterals. Our final true or false question of the day is true or false, all rhombi are squares. So again, if we look at this, if we look at our families, we have rhombi and squares over here. Rhombi do not fall within the square circle. So not all rhombi are squares. The only rhombi that are squares have 4 right angles. That's the only time that a rhombi is a square, is if all 4 angles are right angles. With that being said, we are finished for today. If you guys have any questions or need anything, please let me know. Other than that, thank you guys so much for watching. Have a great rest of your day.